Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is the mechanical properties of squirrel cage induction motors. Our objective is to examine the mechanical properties of the most popular three-phase AC motor in the known universe, the squirrel cage induction motor. We'll examine the construction and theory of operation of squirrel cage induction motors, as well as examine their torque and speed profiles. I have been looking forward to this lecture for quite some time, as I'm certain you have as well. Without overstating their importance, squirrel cage induction motors make society function. They are the actuator of choice for numerous applications and are found absolutely everywhere. As the term frisbee is synonymous with flying disc, and juggalo is synonymous with dirty, paint-huffing subhuman, when people use the term motor, they most likely mean squirrel cage induction motor. They are simply that popular. Unless explicitly stated otherwise, you can assume every time I say motor, I mean squirrel cage induction motor. The popularity of squirrel cage induction motors stems from several identifying characteristics. Principally, squirrel cage induction motors are inexpensive, easy to manufacture, relatively efficient, and necessitate no electrical connections to the rotor. The simple fact that squirrel cage induction motors don't require electrical connection to the moving rotor means they are mechanically simple, reliable, and don't require much maintenance. In fact, squirrel cage induction motors are so reliable, you often see motors installed 20 or 30 years ago regularly performing the same task day after day. If only the crap they make nowadays could last so long. Let's first examine the construction of a three-phase AC squirrel cage induction motor. Like all motors, the principal element of a squirrel cage induction motor are the stator and the rotor. The stator is the stationary part, and the rotor is the rotating part. Get it? Stator, stationary, rotor, rotating. The stator of a squirrel cage induction motor, for all intents and purposes, is absolutely indistinguishable from a stator in a wound rotor induction motor, an electrically excited synchronous motor, or a permanent magnet synchronous motor. They all do the same thing. When excited by three-phase AC, the stator produces a rotating magnetic field. We learned in the rotating magnetic field lecture, available at the Big Bad Tech channel, the synchronous speed, i.e. the speed of the rotating magnetic field produced by the stator, is directly proportional to the excitation frequency and inversely proportional to the number of pole pairs per phase. Long story short, increased frequency and synchronous speed will increase. Conversely, decreased frequency and synchronous speed will decrease. Conversely, if we were to increase the number of pole pairs per phase, synchronous speed would decrease, and if we decrease the number of pole pairs per phase, synchronous speed would increase. If we're stuck using a fixed excitation frequency, let's say 60 Hz in the United States, this results in certain predictable synchronous speeds. A motor with 2 pole pairs per phase, or a single pole per phase, operated at 60 Hz would have a synchronous speed of 3,600 RPM, whereas a motor with 4 pole pairs per phase, or 2 poles per phase, operated at 60 Hz would have a synchronous speed of 1,800 RPM, whereas a motor with 6 pole pairs per phase, or 3 poles per phase, operated at 60 Hz would have a synchronous speed of 1,200 RPM, and so on. These same motors, operated at a reduced excitation frequency of 50 Hz in the EU, in a country with a functional government and working healthcare system, would have proportionally reduced synchronous speeds. Used to be manufacturers would offer a selection of motors with a wide range of numbers of pole pairs per phase. However, the advent of a power electronics device known as a motor drive, a variable frequency drive, VFD, or inverter that can vary excitation voltage magnitude and frequency has largely reduced the need for this level of variety. Oftentimes, the user can simply purchase an inverter-rated motor with a fixed number of pole pairs per phase, and then use a motor drive to vary excitation frequency and thus rotational speed. Lower frequency output means a slower synchronous speed, whereas higher frequency means a faster synchronous speed. Inverter-rated, by the way, means a motor stator with sufficiently robust wiring and insulation that can withstand the higher voltage spike produced by motor drives and can run at very slow speeds without overheating. We'll examine motor drives in later lectures. Like I said earlier, squirrel cage induction motors, wound rotor induction motors, electrically excited synchronous motors, and permanent magnet synchronous motors, for all intents and purposes, have the same type of stator. Really, only the rotor distinguishes one type of motor from the other. The title squirrel cage induction motor implies 2 distinguishing rotor characteristics. Number 1, it looks like a squirrel cage or a hamster wheel. The core of a squirrel cage induction motor rotor consists of a cage-like structure enclosed in laminated iron sheets to concentrate the magnetic field. The conductive cage is often formed of copper or cast aluminum and is astoundingly simple and inexpensive to make. Imagine conductive bars spanning the length of the rotor, linked together with two conductive rings forming a cylindrical cage-like structure. You can't really see the cage inside a real squirrel cage induction motor because it's buried in laminated sheets of iron to concentrate the magnetic field. Number 2, squirrel cage induction motors operate off the principle of induction. The rotor cage has no physical electrical connection to the stator. The rotor and stator are isolated from one another, just like the primary and secondary windings of a transformer. In fact, squirrel cage induction motors were often referred to as rotating transformers in their early developmental stages. One can think of the stator as the primary winding and the rotor as the secondary. When current flows in the primary stator winding, it creates a magnetic field which interacts with the secondary winding on the rotor, such that current is induced to flow in the rotor. The resultant rotor current produces its own magnetic field, which is then attracted to the stator rotating magnetic field and pulled or dragged along with it. Because of the numerous interactions involved, this might take a little thought and imagination on your part. Feel free to rewind or replay this next part as many times as you need to let it sink in. Consider one pole pair inside the stator where the rotating magnetic field is revolving clockwise, and a cross-section of two conductive bars inside the rotor cage. The pole pairs establish a magnetic field oriented north to south between them. As the rotating magnetic field sweeps clockwise, this would be equivalent to keeping the magnetic field stationary and pushing the two conductive bars counterclockwise. I say again, as the rotating magnetic field sweeps clockwise, this would be functionally equivalent to keeping the magnetic field stationary and turning the two conductive bars counterclockwise. There is relative movement of a conductor in a changing magnetic field. Current will be induced in these conductors via the right-hand generator rule. An application of the right-hand generator rule demonstrates induced conventional current in the top bar comes out of the screen, signified by a dot, and induced conventional current in the bottom bar would go into the screen, signified by a cross. This is the first half of the process. The rotating magnetic field on the stator has induced current on the rotor. The current flowing in the rotor bars creates its own magnetic field. Via the right-hand corkscrew rule, the magnetic field produced by the current in the top bar rotates counterclockwise. Similarly, via the right-hand corkscrew rule, the magnetic field produced by the current in the bottom bar rotates clockwise. The magnetic fields on the stator poles and the rotor will interact with one another. The magnetic field on the left of the top bar is aiding, whereas the magnetic field on the right of the top bar is opposing. These fields coalesce such that there are more lines of magnetic force on the left of the top bar. Similarly, the magnetic field on the left of the bottom bar is opposing, whereas the magnetic field on the right of the bottom bar is aiding. These magnetic fields coalesce such that there are more lines of magnetic force on the right. The unified magnetic field acts to push the top bar right and the bottom bar left. This twisting force results in clockwise rotor movement in the same direction of the rotating magnetic field produced by the stator. You may wish to rewind and watch that sequence again. Long story short, current is induced on the rotor by the stator rotating magnetic field. Then the resultant rotor current and its associated magnetic field interacts with the same stator rotating magnetic field such that the rotor is twisted or dragged along with it. The last half of the sequence can also be more succinctly explained using the left-hand motor rule, which states a current-carrying wire in a magnetic field will feel a resultant force. Fingers of the extended left hand are oriented north to south, and conventional current leaves the left palm. Here the left thumb indicates the direction of travel. The left-hand motor rule applied to the conductive bar on the rotors similarly demonstrates the top bar moves right and the bottom bar moves left, twisting or dragging the rotor along clockwise in the same direction of the rotating magnetic field produced by the stator. Again, I'm encouraging you to rewind this sequence as many times as you need to let it sink in. Lest you think that's it, there's a third phenomenon known as counter-electromotive force that takes place that I've yet to discuss. Key to this series of interactions between magnetism, electricity, and movement is the important qualifier, changing magnetism. Induction does not occur if the magnetic field doesn't change. We saw how the stator rotating magnetic field sweeps through the conductive bars on the rotor. This act of being passed by the rotating magnetic field means the conductive bars on the rotor experience a changing magnetic field and thus experience induced current. As a result, the rotor twists or chases after the stator rotating magnetic field. This observation explains an important property of squirrel cage induction motors, and for that matter, all induction-style motors. That property being, induction motors do not rotate at synchronous speed, but rather lag behind synchronous speed, even in the unloaded state. I say again, induction motors do not rotate at synchronous speed, but rather lag behind synchronous speed, even in the unloaded state. To put it another way, the stator rotating magnetic field is always ever so slightly faster than the rotor, such that the stator rotating magnetic field regularly catches up with and overlaps the rotor. To use a rather apt analogy, consider Captain America and Falcon running laps in the movie Winter Soldier. If you haven't seen Winter Soldier yet, pause the lecture and go watch it. I will not have anyone that deficient of culture in my class. Matter of fact, I need you to watch all 23 movies in the Marvel Cinematic Universe if you haven't done so already. There's probably 50 by now, so get cracking. Give yourself some time because you probably want to watch Thor Ragnarok twice. Anyways, you recall Sam Wilson is giving it all, running laps, and along comes Captain America running the same circuit but a much faster pace, and he repeatedly passes him. Captain America is the stator rotating magnetic field. Sam Wilson is the rotor. They're both running laps, but they're out of sync with one another because Captain America is slightly faster, which is what you'd expect given they injected him with a 1940s chemical cocktail of Red Bull, Viagra, and speed and cooked him in a microwave just to make sure. If my cartoonish graphics didn't do the trick, here's a quick demonstration of induction I never tire of. Consider a large ball of copper. Let's pretend the copper ball is the rotor. Is copper magnetic? When I place a strong permanent magnet in close proximity to the copper ball is neither attracted nor repulsed by the magnetic field. So no, copper in ordinary circumstances isn't a magnetic material. Now, consider the copper ball's reaction to a changing magnetic field meant to simulate the rotating magnetic field in the stator. As the changing magnetic field sweeps through the copper ball, it induces current on the ball. The current flowing in the ball creates its own magnetic field, which interacts with a moving magnetic field such that the ball is twisted or dragged along with it. This illustrates the motor action inside a squirrel cage induction motor. Pretty cool, eh? One could observe similar effects given a different frame of reference. Consider a stationary magnetic field and a moving conductor. As the ball is spun, it experiences a relative movement of the magnetic field and induction again occurs. This illustrates generator action inside an asynchronous generator. We'll examine asynchronous generators in later lectures. Long story short, the rotor is out of sync with the stator for induction machines. This is what creates the changing magnetic field necessary for the induction process. And it's largely for this reason induction-style motors are sometimes called asynchronous motors, meaning the rotor is not synchronized with the stator rotating magnetic field, but rather lags behind it in motor mode. We'll examine generator mode, where the rotor leads the stator in later lectures. This degree of lag or lead is sometimes called slip, and typically expressed as a percentage of synchronous speed. Percentage slip can be calculated as the difference between the rotating speed of the rotor and the synchronous speed over the synchronous speed times 100%. Consider a squirrel cage induction motor with a synchronous speed of 1,800 RPM. In the unloaded condition, let's say the rotor turns at 1,780 RPM. As one might expect, this is sometimes referred to as the no-load speed. The rotor lags synchronous speed by 20 RPM, where 20 RPM is roughly 1.1% of synchronous speed at 1,800 RPM. In the unloaded condition, the rotor is spinning relatively quickly, however it exerts no torque, i.e. it's unloaded or free spinning. An application of the mechanical power formula, where mechanical power is equal to torque times rotational speed over 9.55, demonstrates the motor produces no mechanical power in the unloaded condition. If we were to plot torque and mechanical power output on the vertical y-axis and speed on the horizontal x-axis, we'd be at the far right of the motor's operational curve. Notice the horizontal x-axis doesn't start at 0 RPM, but rather the horizontal axis spans 1200 to 1800 RPM. I'll explain why in a moment. In the unloaded condition, the motor slightly lags synchronous speed of 1800 RPM at roughly 1780 RPM and produces no torque and no mechanical power. Consider the same motor in the loaded condition, exerting 1.1 Newton meters of torque at let's say 1710 RPM. The rotor now lags synchronous speed by 90 RPM, where 90 RPM is 5% of synchronous speed. In the loaded condition, oppositional torque increases, the rotor slows, and slip increases. Application of the mechanical power formula demonstrates the motor produces roughly 197 watts of mechanical power, slightly more than a quarter horsepower. If we're to define this as typical operating conditions this particular motor was designed for, we might expect to see a rated speed of 17 RPM and a rated mechanical power output of roughly 197 watts in the motor nameplate. As one might expect, this is sometimes referred to as the rated speed where the motor produces its rated torque and its rated mechanical power output. If we were to plot torque as a function of speed, we'd see a roughly linear transition from 0 Newton meters at the no-load speed of 1780 RPM up to 1.1 Newton meters at the rated speed of 1710 RPM. Similarly, if we were to plot mechanical power as a function of speed, we'd also see a roughly linear transition from 0 watts at the no-load speed at 1780 RPM up to 197 watts at the rated speed of 1710 RPM. There's understandable limits to this linear relationship of increased oppositional torque and slip. One might expect this motor to experience some peak torque output and then a subsequent decline. Let's say this motor's peak torque output of 2.2 Newton meters occurs at 1260 RPM. An application of the mechanical power formula demonstrates the motor producing 2.2 Newton meters of torque at 1260 RPM yields roughly 290.3 watts of mechanical power. This is not peak mechanical power output, but it is peak torque. Any increase in slip would have the motor enter what is known as the breakdown region, where torque output actually decreases as rotational speed decreases. It is for this reason the peak or maximum torque produced by an induction motor is often referred to as the breakdown torque. You recall, mechanical power is the product of torque and speed. Peak mechanical power output does not occur at peak torque, nor does it occur at peak speed, but rather the product of torque and speed produces a maximum. This ordinarily occurs just before peak torque. Let's say this motor produces peak mechanical power output of 300 watts at 1365 RPM. An algebraic rearrangement of the mechanical power formula, solving for torque, would demonstrate that the motor produces roughly 2.1 Newton meters of torque at peak power conditions. Before we examine the breakdown region, consider the plot of torque as a function of rotational speed from 0 Newton meters to maximum torque. It'd be easy to describe torque versus speed as roughly linear inside this region, especially at or near the rated conditions. Yes, it does taper off as it nears breakdown. However, if you ignore the roll-off, it's kind of linear. If you think about it, the motor is kind of behaving like you'd expect. Load the motor, it slows down. Unload the motor, it speeds up. If we define the motor's rated condition as producing 1.1 Newton meters of torque at 1710 RPM, or 197 watts of mechanical power, any reduction in load would see the motor producing less than 1.1 Newton meters, rotating faster than 1710 RPM, and producing less than 197 watts of mechanical power. At the rated output, unless the motor is ordinarily capable of running in this fashion without issues, more or less continuously, unless the motor is specifically designated as having an intermittent duty cycle. Operating at anything less than the rated conditions means the motor is underloaded. Conversely, any increase in load beyond the rated condition would see the motor producing more than 1.1 Newton meters, rotating slower than 1710 RPM, and producing more than 197 watts of mechanical power. Above the rated output, the motor is in an overload condition and isn't intended to operate in this fashion for any length of time without the risk of damage. An example of a brief but permissible overload would be an electrical saw hitting a knot in a piece of wood. The motor experiences a brief overload event, but the overload isn't sustained for any length of time. Motors are ordinarily operated at or around the rated conditions. Inside the breakdown region, things go south rather quickly. Expanded plots of torque and mechanical power as a function of rotational speed might look something like this. Any decrease in rotational speed or increase in slip beyond the breakdown torque will see the motor's usable torque decrease, settle, and then briefly rise again as speed decreases and slip increases. This breakdown region corresponds with decreased mechanical power output. At the locked rotor condition, i.e. a rotational speed of 0 RPM, the motor can produce a respectable amount of torque, let's say 1.4-ish Newton meters. Torque is respectably high, but the shaft isn't moving. An application of the mechanical power formula at locked rotor conditions demonstrates the motor yields 0 watts of mechanical power. The complete plots of torque and mechanical power for the entire range of rotational speed reinforce our earlier observations. Don't mechanically overload the motor, and if you do, don't overload it for very long. Not only will efficiency be poor, we've yet to discuss electrical properties and efficiency, the motor is not operating at peak conditions. Again, ideally a motor is intended to operate at or around its rated conditions specified in the motor nameplate. Inside this ideal region, it behaves pretty predictably. Load it up, it slows down. Unload it, and it speeds up. The speed torque profile we examined is meant to represent a NEMA Design B motor, a commonly available motor suitable for numerous applications like blowers and pumps. Other speed torque profiles exist. The second most common being a NEMA Design D motor. Design D motors are designed for high inertia starts like a crane or a hoist. As evidenced by the speed torque curve, Design D motors produce higher torque at lower speeds. What's nice about these generic speed torque curves is if we were to plot them using not specific numerical data, but rather percentage of synchronous speed and percentage of rated torque and percentage of rated power, we can make educated guesses about points in the speed torque curve. If we were to define the vertical axis as percentage of rated torque and the horizontal axis as percentage of synchronous speed, Design B and D motors might look something like this. A Design B motor is expected to produce 100% of its rated torque at 1 to 5-ish% slip, depending on size and manufacturer. Assuming 3% slip, this means 100% rated torque occurs at 97% of synchronous speed. Design B motors ordinarily experience a peak breakdown torque around 200% of its rated torque, somewhere around 80-ish% of synchronous speed. Finally, a Design B motor might produce 150-ish% of its rated torque at 0% of synchronous speed or at locked rotor conditions. In contrast, a Design D motor will produce 100% of its rated torque at an increased slip. Assuming 10% slip, this means 100% rated torque occurs at roughly 90% of synchronous speed. Finally, a Design D motor produces around 300% of its rated torque at 0% of synchronous speed or at locked rotor conditions. These speed torque curves imply that a Design B motor experiences peak mechanical power output. The product of torque and rotational speed occurs at a faster rotational speed, whereas a similarly rated Design D motor will experience peak mechanical power output at a much slower rotational speed. Note the B power curve has a more significant rightward lean than the D power curve, not as much. This again points towards the intended purpose of these different types of motors. Design D motors favor the lower speed, higher slip, higher torque applications one would expect for higher inertia loads. Besides the speed torque curves, there are two other fundamental differences between Design B and Design D motors. The first being their rotors. Design D rotors, in comparison to Design B rotors, feature conductive bars with higher resistance. I'll explain in later lectures how a wound rotor induction motor, another type of induction motor, can vary rotor resistance to change the shape of the speed torque curve depending upon application. The second noticeable difference between Design B and Design D motors is their efficiency. Again, we've yet to discuss electrical properties and efficiency. However, Design B motors are relatively efficient, whereas Design D motors, not so much, meaning a Design D style motor will consume more real electrical power input to produce usable mechanical power output. Now, before you take the time to memorize these charts, let me make this important disclaimer. They are only reasonably accurate. A specific manufacturer might sell Design B motors that do not produce 100% of rated torque at exactly 97% of synchronous speed, but rather at 98% or even 95%. An entirely different manufacturer might sell Design D motors that don't produce exactly 300% of rated torque at locked rotor conditions, but rather 280%. You get what I'm saying. Additionally, there's a significant performance difference between small and large motors, where the dividing line between small and large is somewhat arbitrary. Smaller fractional horsepower motors might exhibit more slip at the rated conditions, whereas larger integral horsepower motors might exhibit less slip at the rated conditions. Fractional horsepower motors, by the way, means motors with output of less than 1 horsepower. Examples being 3/4, half, third, and a quarter, and so on. Get it? Fractions. Conversely, an integral horsepower motor means a motor with 1 horsepower output or more. Examples being 1, 2, 3, 5, and so on. These larger motors might exhibit less slip at the rated conditions than these charts suggest. This being said, these charts are still pretty good, and you can use them as a general guideline for what you might encounter in the field. If you want accurate information, you'd have to consult the manufacturer's datasheet for the specific motor of interest. Assuming these charts are accurate, we can make some educated guesses how a certain motor might operate. Consider a 2 horsepower Design B motor with a synchronous speed of 1800 RPM. We know nothing else about this motor. Using the generic chart, we might reasonably expect this motor will experience rated conditions at maybe 97% of 1800 RPM or 1746 RPM. This would be the rated speed you'd see on this motor's nameplate. Again, it might be more, it might be less, however, let's assume this is true. At the rated conditions, this motor is known to produce 2 horsepower of mechanical power output. A unit conversion demonstrates 2 horsepower as equivalent to 2 times 746 or 1,492 watts. An algebraic manipulation of the mechanical power formula, solving for torque, demonstrates that torque at the rated conditions is roughly 8.2 newton meters. 8.2 newton meters therefore represents 100% of rated torque. At peak power output, we might reasonably suspect this motor is capable of generating 150% of 2 horsepower or 3 horsepower. Finally, we might reasonably expect this motor to exert a maximum of, let's say, 2 times 18.2 newton meters or 16.3 newton meters, and be capable of exerting, let's say, 1.5 times 8.2 newton meters or roughly 12.2 newton meters at the locked rotor conditions. Let's try the same thing for a design D motor. Consider a 3 horsepower design D motor with a synchronous speed of 1200 RPM. We know nothing else about this motor. We might reasonably expect this motor to experience rated conditions at maybe 90% of 1200 RPM or 1080 RPM. This would be the rated speed you would see on this motor's nameplate. Again, it might be more, it might be less, however, let's assume it's true. At the rated conditions, this motor is known to produce 3 horsepower of mechanical power output. A unit conversion demonstrates 3 horsepower is equivalent to 2,238 watts. An algebraic manipulation of the mechanical power formula, solving for torque, demonstrates torque at the rated conditions is roughly 19.8 newton meters. 19.8 newton meters therefore represents 100% of rated torque. At peak power output, we might reasonably suspect this motor capable of generating 150% of 3 horsepower or 4.5 horsepower. Finally, we might reasonably expect this motor to be capable of exerting 3 times 19.8 newton meters, roughly 59.4 newton meters at locked rotor conditions. That's more than enough torque to yank your balls right out of your sockets. Again, these might be reasonable approximations of what you might expect, and actual motor performance will vary widely. Always consult the manufacturer datasheet for your particular motor of interest. The curious among you may ask, what do designs A, C, and E speed torque curves look like? The speed torque curves for A's and E's, for all intents and purposes, kind of look like B's. This is an obvious overgeneralization. There are subtle mechanical and electrical differences between these types of motors. However, at this early stage in the game, these subtleties may escape your notice. Design C's kind of look like a B and a D motor had a baby. Design C's produce higher starting torque than B's, but not as much as D's. Their rated torque, however, occurs at a lower degree of slip, similar to that of a B. You'd think everyone would use well-organized and well-labeled charts, but they don't. Often motor manufacturers try to cram a bunch of information on one page and use one color to do so. Here's an example of what you might encounter in the field. This is the datasheet for a 1 horsepower design B motor intended to operate using 460 volt 3-phase AC. Look at all those dashed lines. Let's see if we can make sense of this foolishness. I know it may seem confusing at first, but there's a lot of important information on this plot, and given some practice and repeat exposure, it's relatively easy to interpret. The key data point to remember is that this is a 1 horsepower motor. The horizontal x-axis isn't speed, it's percent power output, or 100% of rated power output, or 1 horsepower, is this vertical line right here. Anything to the right of the vertical 1 horsepower line is an overload condition. Anything on the vertical 1 horsepower line is the rated condition, and anything to the left of the vertical 1 horsepower line is an underloaded condition. We see this motor can produce 0% up to 150% of 1 horsepower or 1.5 horsepower at peak conditions. The datasheet plots torque using a dashed line, RPM using another type of dashed line, current using another type of dashed line, efficiency in a solid line, and power factor using another type of dashed line. Again, we haven't explored electrical properties yet. However, realize every piece of data on the motor nameplate is specified at 100% of rated power output, or 1 horsepower. I know there's a lot of dashes dashing all over the place, but the intersection of each dashed line with a vertical 1 horsepower line is most likely what is specified in the motor nameplate. For example, if a regular dashed line means rotational speed, it looks like at 100% of rated power, the rated speed might be around 1770 RPM. A rotational speed of 1770 RPM for a synchronous speed of 1800 RPM represents a slip of only 1.6%. This is the level of variability I was referring to earlier one might expect to observe between different motor manufacturers and different motor sizes. In fact, there's a lot of variability shown in this example, as we'll soon learn. You note the vertical y-axis specifying rotational speed starts at 1800 RPM and only goes to 1700 RPM. Basically, this chart is only presenting data on the extreme right-hand side of the speed-torque curve. Why? Because that's where you should operate this motor, i.e. around the rated conditions. You'll note the dashed rotational speed slopes downwards, left to right. This makes sense. Under loaded regions to the left of the rated conditions, the motor will speed up, whereas overloaded regions to the right of the rated conditions, the motor will slow down. If dash double dash represents torque, this motor exerts around 3 pound-foot of torque at the rated conditions. What in the hell is a pound-foot? Google says it's an archaic torque measurement used by ignorant savages that happens to equal around 4.1 Newton meters. You note the dash double dash torque line slopes upward left to right. It makes sense. Under loaded regions to the left of the rated conditions, the motor exerts less torque, whereas overloaded regions to the right of the rated conditions, the motor exerts more torque. Now that we have rotational speed and torque data at the rated conditions, let's examine mechanical power output and efficiency. An application of the mechanical power formula demonstrates 4.1 Newton meters of torque at 1770 RPM represents 759.9 watts of mechanical power. If 1 horsepower is equal to 746 watts, 759.9 watts is just above 1 horsepower, as we might expect. It's a 1 horsepower motor. If this solid line represents efficiency, this motor appears to be maybe 86% efficient at the rated conditions. Given the efficiency rating and mechanical power output, we can solve for the necessary real power input consumed by this motor at the rated conditions. An algebraic manipulation of the efficiency formula, solving for input power, demonstrates we will most likely need to consume at least 883.6 watts of real electrical power. Let's check if we're right. Again, we haven't examined electrical properties in great detail just yet. However, let's perform some quick calculations at the rated conditions as a warm-up exercise for the following lectures discussing electrical properties of squirrel cage induction motors in greater detail. If this dashed line, big surprise, it's dashed, represents current, it looks like this motor draws maybe 1.8 amps at the rated conditions. If this other dashed line represents power factor, it looks like this motor has a power factor of 0.62 at the rated conditions. This motor is intended to operate using 460 volt 3-phase AC as a balanced load. As such, we can make use of the single wattmeter method to determine power, where apparent power is square root 3 times line-to-line voltage times line current. Substituting our given values yields 1,434.1, or roughly 1.4 kilovolt amperes of apparent power. Real power is apparent power times power factor. Roughly 1.4 kilovolt amperes times 0.62 yields roughly 889.2 watts of real electrical power, extremely close to the 883.6 watts we calculated earlier using mechanical power output and efficiency. It all makes sense. Lastly, since this motor datasheet does not include a complete speed torque curve for the whole range from 0 to 1800 RPM, it specifies a couple pieces of data, namely the breakdown torque listed as BDT, which specifies as a maximum of 16.5 pound-foot, which Google says is roughly 22.4 Newton meters, much higher than the 200% we might expect, which just goes to show you that expectations are there to be crushed. Additionally, it says it has an LRT, or locked rotor torque, of 11.4 pound-foot, which Google says is roughly 15.4 Newton meters. This is much higher than the 150% rated torque we might expect. Again, always consult the manufacturer's datasheet for the specific motor of interest for the most accurate data. Lastly, the motor includes an additional data point called PUT, which stands for pull-up torque, which is kind of the lower belly of a speed-torque curve for a Design B motor. Now that I mention it, I probably should discuss the significance of pull-up torque for Design B squirrel cage induction motors. Close inspection of a general speed-torque curve for a Design B squirrel cage induction motor shows torque kind of dips down between lock rotor torque and breakdown torque. This low point in the bottom of the valley is the pull-up torque. I think the easiest way of describing the significance of pull-up torque is using a simplified example. Consider a motor with a locked rotor torque of 1.4 Newton meters, a pull-up torque of 1.2 Newton meters, and a breakdown torque of 2 Newton meters, and a rated torque of 1 Newton meter. I don't want this to devolve into a physics lesson, but consider an occasion in which the motor needs to move something that exerts a constant 1 Newton meters of counter torque. Upon closure of a full voltage starter, the motor easily yanks the applied load to a start. Given there is sufficient locked rotor torque, the motor quickly accelerates and transitions to the rated speed. In summary, if the applied load is below the pull-up torque, i.e. the dip in the speed-torque curve, the motor will accelerate until it reaches a stable speed and torque point on the curve. Not so if the applied load is above the pull-up torque. Consider the same motor moving something that exerts a constant 1.3 Newton meters of counter torque, i.e. below the locked rotor torque, but above the pull-up torque. Upon closure of a full voltage starter, the motor does yank the applied load to a start, but then the motor ceases to accelerate and stalls just shy of the pull-up torque. Unless someone gives the load a good kick, this motor will remain in an undesirable overloaded condition. Lastly, the motor explicitly specifies inrush current or locked rotor amperes, LRA, one might expect to experience upon closure of a full voltage, direct on line or across the line starter. Ordinarily, we might expect inrush to be roughly 6 times rated current. If this motor is expected to draw 1.8 amps at rated conditions, we might expect a brief surge of 6 times 1.8 amps, or 10.8 amps of inrush. This approximation isn't really true. Looks like the datasheet specifies this motor will draw a whopping 15.7 amps, 8.7 times the rated current, i.e. more than our 6 times shortcut calculation suggests. We'll examine inrush calculations and the electrical theory of inrush in later lectures. Long story short, all the information is right there on the datasheet. All you got to do to interpret it is to learn to distinguish between a regular dash line, a long dash line, a short dash line, a double dash line, a dotted line, and a solid line. If this datasheet was something I need to refer to on a regular basis, I'd break out a box of colored pencils and make sense of it real quick. Alright, that's about it for this introductory lecture on the mechanical properties of squirrel cage induction motors. I was going to go right into the electrical properties, however this lecture is getting a little long already, and a complete discussion of electrical properties will only make it longer. We'll examine electrical properties like current, efficiency, and power factor at and at other than the rated conditions in greater details in later lectures. In conclusion, this lecture examined the mechanical properties of squirrel cage induction motors. We discussed squirrel cage induction motor construction and basic theory of operation, examined speed torque curves for Design B and Design D motors, and waded through a swamp of dashes on a motor datasheet. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.